Good morning. Today we will discuss about differential amplifier. In last few classes we have covered the power amplifier, and today we will discuss about differential amplifier. We already have covered we in previous class and about we know about the amplifier, right. So, the basic structure of any amplifier is differential amplifier. Okay. So, this differential amplifier we can design with the help of BJT or with the help of MOSFET. Now, this structure, this is known as the resistive load differential amplifier. Okay. So, Q1 and Q2, these are the main matching driver. Okay. So, this is my driver Q1 and Q2, they should be symmetrical, and the load, you see, this is RD is my load and this my driver, right. And this circuit, this is a current meter, you can, this is a current source, you can see, this is for biasing purpose. So, this is called, see, it is in the below of the Q1 and Q2, right. So, there are two names, one is tail current source, another is bias current source. So, you can say tail current source or bias. Now, suppose you are providing a DC voltage only. Okay, you see both of the gate is shorted, you see this dot means short. Okay. So, sometimes we draw like this, right, that to show that it is not shorted, and sometimes we also show this dot as a short. So, this as there is no dot, this is not a short. Okay, do not get confused. You may think that this is a short because the wire is coming over it, but this dot is actually where the connection is. Okay. So, this gate and this gate, they are shorted to which voltage? VCM, V common mode voltage, CM stands for common mode voltage. So, this is a DC voltage. So, you understand both of the MOSFET are having same voltage. So, their VGS is also same. So, their I should be also same, right. Now, what should be their I? The total current is I. So, each of the branch will carry I by 2, agree. So, this is the my first condition. What is the first condition? You know that to design any amplifier, first condition is to DC bias, provide the proper DC biasing, so that both of the transistor, if it is a MOSFET, it is in saturation, right. So, this VCA, my purpose is to provide a DC voltage, so that both of these MOSFET is in saturation region, and at DC condition, when both of the gate voltage is same, they carry equal amount of current. So, each of them will carry I by 2 and the summation of that will become equal to I. So, now you can understand the purpose of the current source I. The I is telling that your limit is that, this is your maximum current, it is fixed. Okay. So, this is actually taking control, that this is defining that you cannot change. Now, suppose if I increase this and decrease this, now I am adding on top of the DC voltage, one voltage is increasing, another voltage is just phase shifted opposite to invert to that. So, suppose this is VG1 and this is VG2. So, one voltage, the voltage at Q1 is increasing. So, what will happen to I1? I1 will also increase or decrease? Increase. If I1 is increased, what will happen to the VD1 output of this branch? It will increase or decrease? It will decrease, because this resistive drop will increase and it is subtracting. So, V out will decrease. So, you see my input and output, this branch, same branch, they are phase shifted, right, just like the common source minus GMRD. So, if input is increasing, output of this branch is decreasing. So, what will happen to the opposite branch? It should increase, right, because you see total current is fixed, I, one current is increasing. So, what will happen to the other current? It should decrease, so that total current is constant. So, if this voltage is decreasing, what will happen to this voltage? It will increase. So, these and these are in phase. So, this VI1 and VO2, they are actually in phase. So, my del V should be VO2 minus VO1, agree? So, let us see it in this second. So, this is a differential amplifier with BJT, same structure, no problem. So, there the current source is modeled with a resistance, that is also okay. Roughly it will behave like a current source, or we can model it with a current source, but for this moment you assume that this is a constant current source. So, if I increase this voltage, this is say VI1. So, this output will be out of phase, but this output will be in phase. So, you see here this input and this output, they are in phase shifted, one is increasing, other is decreasing at the moment, or opposite, you can say 180 degree phase shifted. So, this input and this output, they will be out of phase, right, but if you consider that here they have taken VO1 minus VO2, actually if we take VO2 minus VO1, then they will be in phase. So, this you see, this output VO1 and VO2, they are phase shifted, right. So, if we subtract them, so they will be double, na. If you have a V and you have a minus V, right, you can think like that. One arm you are getting output V, in other arm you are getting phase shifted, so minus V. If you subtract them, they are actually getting added. So, you see this output, this is the differential output, this is a single ended output. Single ended means only this branch I am thinking, this is single ended, only this branch I am thinking, but this is VO1 minus VO2, this is called differential in, differential out. So, if you subtract the output, it is actually getting doubled. This is another advantage of the differential amplifier. So, what we are saying, that suppose I am giving this is my Vd is equal to say Vi1 minus Vi2, this is the differential input. Vd is the difference of Vi1 and Vi2. Okay. So, if I define my Vo is equal to Vo2 minus Vo1, they will be in the same phase and amplified. And if I plot Vo2, Vo2 will be in same phase. So, this is Vo and this will be Vo2, and Vo1 will be out of phase of Vo2, understood. And if we subtract them, we will get if this is V, del V, this should be twice del V. So, this is our differential amplifier. So, this op amp, which is basically a basic topology, is a diff amp. We know that we have a 2 input and actually we are having 2 output. If we subtract them, we get a single output. Okay. So, this output is actually, you can think of VO2 minus VO1. Now, if I want to plot the transfer function, we know that it is like a linear, right. This is the portion when it is working as an amplifier. Which amplifier? Which is a linear amplifier. We know this curve, this slant line means that I will be getting a amplification. This slope is my gain, right, and I will be reaching a point where it will get flat, saturate. So, this range, this is my range when if input is within this limit, I will get a amplified output, but if I cross this range, what will happen? My output will get clipped. So, I cannot cross this linear range. Okay. So, this range is my linear range. Here you see, even if my input is increasing, output it cannot increase, it is saturated. Okay. So, let us think this way. Suppose your this differential voltage, this is VO1, this is a VI1 minus VI2. So, this is my differential voltage. If I am making it positive, more positive, this positive terminal, I am giving more voltage than the negative terminal. So, what will happen? It will increase and sometimes it will go to latch to plus VCC. Similarly, you think the opposite way, that I am increasing the negative voltage. So, Vd is decreasing, decreasing, output is also decreasing, but there is a limit. After a certain range, it will go and saturate to minus V. Agree? So, this is my transfer characteristic, this is my transfer characteristics. What is the meaning? Transfer characteristics? V0 versus V in, okay. Output versus input. So, you see the difference. This is y axis is output voltage, x axis is input voltage. Which input voltage? Differential input voltage. Which output voltage? Differential output voltage. But this plot, if you say, this is y axis is amplitude voltage, x axis is time, this is a transient response, right. This is time, with time how the voltage is moving, right. So, this is known as the timing analysis or transient analysis. My x axis is time, with time how my output is looking, but in this plot, this is what my input, x axis DC, some DC voltage. So, this is known as the DC plot. Previous one was transient plot. Why transient? Because x axis was variable was time. Here the x axis, the variable is DC voltage. So, this is a DC plot, that was a time plot. If x axis is a frequency, it will be a AC plot or frequency plot. Understood? How many variations? If x axis is a time, it is a transient analysis. If x axis is a DC input, it is a DC analysis. If x axis is a frequency, this is a AC analysis. Where do we see that frequency AC analysis? In which kind of chapter we have seen? We have seen in filter, right, oscillator, because frequency was of important, right. So, these are small thing, but this adds some value to your learning. So, we have discussed what will happen, right. So, now let us discuss the DC response. Okay. So, what we said that if we give the same DC to the both of the input, they are common, right, they are same, equal. So, this voltage is known as the common mode voltage, or this response is known as the common mode response. Now, can you tell me what will be the differential voltage in case of VCM? Suppose you have applied VCM to both of the gate, what will be your output voltage VD? If you apply same voltage, VO1 and VO2, they are also should be also same. So, what should be VD? 0. So, if you apply DC voltage, the differential output is 0 because they are same. So, you should have a, if you apply different input means one is increasing, other is decreasing, then you get a amplified output, right. But if you apply the same input, they are ideally 0. So, you get something like this. This is your differential gain by common mode gain is 0. So, what should be this ratio? Ideally it should be infinite. What is this known as? Common mode rejection ratio, CMRR. So, what is this? Differential gain by common mode gain. Now, we have seen that in common mode my differential out is 0. So, this is AV by 0 is equal to, ideally it is infinite for op amp, right. We have seen that ideally it is infinite, but in reality it is very large. Okay. In reality it may not be infinite, but it is very large. So, we say that it is infinite. Now, you have understood that why we say that, okay. Because VCM is same. So, same current I by 2 is flowing, I by 2 is flowing in this branch, I by 2 is flowing in this branch. So, what will be the V0? V0 is equal to VDD minus I by 2 into RD in both of the branch, and if you subtract them it is 0. Okay. So, we can calculate certain things. What we can calculate? That this VCM, suppose this is increasing. So, if you do not have this I, what would happen? Suppose this I is not there, and now you are increasing VCM, what will happen? This I will increase, right, both of the I will increase, branch current will increase, and if it increase, output will also fluctuate, output level, because you are subtracting more current. But what is desired, that even if your input DC output should be dependent on the only signal, not on the DC variation, right. DC is only for biasing, that we have seen, and output should vary only with AC signal. But if we do not have I do not have control. Getting my point? This is my input VCM. Now, suppose I am increasing VCM and I do not have a I, let us consider that this I is not there, this is grounded, this node is grounded. So, what will happen? This VGS is increasing, this VGS is increasing, this I is increasing, this I is increasing. So, this V0 will be decreasing, this will be also decreasing. So, this output previously it was VO common, VOC, this will start to decrease. But what was our original aim? That this DC should not vary, only the AC should vary. But now what is happening? DC even it is starting to fall, or suppose VCM we are moving it to close to 0, then current will be less. So, this output will start to increase. So, this level, output level, if I do not have this current source, I have no control. Now, I have a current source. Now, suppose VCM even it increase, total current is constant. So, my I by 2 this is fixed, they cannot change. So, even if my VCM is changing, my output voltage, output common mode level, output DC, that cannot change. Clear? So, what is the advantage of using this current source? Is it clear or you have any question? Just think about it. Suppose I have this structure. Now, if this VCM is increasing, this output will be decreasing. Why? Because current is also increasing. So, subtraction is more, it will fall. So, this level is now a variable with this input level. I do not have any control, but if I force a bias current here I by 2. So, this current will tell this current, okay, you are fixed now, you cannot change. So, even if my this DC voltage is varying, this current cannot change. Why? Because this is forcing the, what is the meaning of constant current? Even if the voltage is changing, current cannot change, that is the constant current, na. So, this current is forcing this I, that you cannot change. Otherwise, what would happen? I is a function of VGS, as VGS is changing, I should also change. This I is now free, there is no one to control. Okay. So, this is the role of this current source, this is the role of the current source. What is the role? To control the output level, so that output level is fixed. The current cannot, DC current cannot change, AC current can change, but the sum total of the current KCL will always has to be satisfied. So, sum total of the current is constant. Understood? So, this is the job of the current source. So, sometimes you will see a question that what if we do not use the tail current source? What if this node is grounded? Will it still be acting as a differential amplifier? Yes, it will be acting as a differential amplifier, but what will happen? The output voltage level, DC level is always fluctuating. So, it is not a better one, this is the better one. Clear? Now, what we can do more analysis on this is that we can define the maximum level of input voltage and minimum level of input voltage. So, this VCM now you know, even if it vary, my output voltage will be fixed, but there should be a limit, right. So, who will define this limit? That I cannot increase input more than that, I cannot decrease input less than that. What is the governing parameter? What is the governing condition? What we assume initially, that to be a good amplifier, this MOSFET should work in which region? Saturation region, that is the condition. So, the condition is that Q1 and Q2 should be in saturation. If it moves out of this saturation zone, this amplifier will no longer behave like a good amplifier, its linearity will be destroyed, right. The saturation limit you know. So, this zone and this zone, in one it is in entering in linear, in other it is entering in cutoff. If your input common mode voltage is very low, so if it falls below Vt, so this Q1 and Q2, the effective VGS, if it is fall below Vt, they will not carry current, right. So, your output will go to clip 2. If 0 current is flowing, output should be both of the branch VDD, subtract them, 0, minimum possible. Okay. If you increase this VCM too much, what will happen? Gate to source voltage is increasing, you are increasing it. So, let us make it maximum VDD, VGS is equal to VDD. So, VGS minus VT is equal to something, and what will happen if VGS is increasing, my output is what? VGS is I am increasing, current is also increasing. So, VDD minus IDRD, this is decreasing. So, gate voltage is increasing, drain voltage is decreasing. So, it will leave out of saturation region. What is the condition for saturation? VDS should be greater than VGS minus VT. Now, VDS is falling, VGS is increasing. So, there is more chance that it will leave the saturation region. Okay. So, I have a limit of the common mode voltage. This is known as the common mode input common mode range. I cannot change, although I have seen with the use of I said that even if common mode is fluctuating, output level cannot change, but there is a limit. I have a range, beyond that if I go this input common mode voltage, then this Q1 and Q2 they will be out of saturation region, and it will be no longer a good differential amplifier. Okay. So, how to calculate this? We can calculate the current and then calculate all of this. So, what is the current each branch? I by 2 equation, I by 2, this is saturation, half K n dash W by L VGS minus VT whole square, that we know, square law. Okay. And now we can define VGS minus VT as VOV, overdrive voltage. VOV is equal to VGS minus VT, and same thing we can write in terms of VOV and can calculate the VOV, right. We have written this I in terms of half K n dash W by L VOV square. So, what is VOV? Okay, this half get cancelled. So, VOV is equal to square root of I by K n dash W by L, that is a easy simplest equation that we know. And another thing we know that what is my output? VO1 and VO2, that is equal to drain voltage, right. So, this is equal to VD1 is equal to VD2 is equal to VDD minus current into resistance. Current is I by 2, resistance is RD. So, another equation is VD1 is equal to VD2 is equal to VDD minus I by 2 RD. So, these two equations we have, we know. Now, from this we can calculate the maximum limit of the VC max and minimum limit of the VC min. Okay. How? We just described it that we should see that one limit is cut off. So, we will check that this cannot go, so that this VGS is less than VT, this is one condition, and another limit is active region. We cannot increase, so that VDS falls below VOB. Okay. From these two conditions we can calculate this. So, these two are my maximum limit that we can calculate, and this is known as the input common mode range. My VCM can vary, but it cannot vary more than these two limit. So, this is my range, within this I am safe. Okay. Now, let us check about the differential input. Now, suppose I am increasing one input and I am decreasing other input. One input I am increasing, other input I am decreasing. So, what will happen to this branch current? This will increase and this should decrease. Why? So that total current is constant. Clear? I have a constant tail current source. So, this tail current source, this is binding that total current cannot change. Now, on top of the previous DC voltage VCM, so this is actually I am having a VCM here, I am having a VCM here. but for the AC analysis what we do, we consider all the DC are grounded. So, we consider that VCM is not there, but actually it is there. I am doing only the AC analysis. Okay. So, on top of the DC, as we discussed in single stage amplifier, that on the DC bias we will superimpose AC. So, same thing, same concept, but while doing the small signal analysis, what we consider, all the DC sources are removed, right. So, this is grounded, but you can think that this is not actually ground. I have to give the VGS, right, otherwise if it is a BJT I have to give the VB, otherwise it will not work, right. So, what minimum voltage I should give? This VGS plus current for this voltage for this current source. If it is a current source, some circuit will be there, right. So, some drop I have to allocate for that. So, it is, you cannot think that only VGS, VGS is above some circuit. So, suppose this is taking VB. So, VB plus VGS I have to at least provide, clear. Suppose this tail current source is taking a voltage of VB. So, VB plus VGS, that much minimum at least I have to provide, that much DC at least I have to provide. For example, here in this circuit, this current source is implied by this resistance. So, what is the drop? IERE. So, IERE plus VB, that much voltage at least you have to provide. So, do not only think that only VB, this VB is above this voltage. So, this voltage also you have to provide, then only it will work. So, we are discussing that, let us give one differential input. Now, this differential input I can give in many way, right. One is grounded, other I am giving a positive voltage, that is also okay. So, this is a single ended input, other is grounded. Generally in op amp we do that, right. One is grounded, other I am giving input. So, something like that, that is also okay, or we can give a phase shifted input. Now, this equation remains same, only one equation, I is equal to half k n dash W by L VGS minus VT, that is the advantage of the MOS circuit, only one equation. If you know this current equation, rest of the calculation you can derive from this only. Okay. Whatever JM, whatever VOB, whatever V out, all only one equation, only if you know this current equation you are done. Okay. So, you see VGS, I have just restructured this equation. You do not need to remember what is VGS, you just need to remember ID. VGS you can, this is just calculation, right. So, I will not stress on this VGS equation, I will stress only this equation, rest of the stuffs you can step by step you can calculate, do not worry. Okay. So, VGS is equal to VT plus this square root of 2 I so VOB, and what is VID max? VID max is VGS plus VS, and just this equation, VDS should be greater than equal to VGS minus VT. From this you will get the VD and this condition. Okay. Now, you can understand, if your total current is fixed to I, so if one is increasing, other should decrease. So, that total current is always I. So, at the middle point you see both of them are same to what value? I by 2. So, that again sum is always I. What is the maximum value now? I. So, it cannot go beyond I, because I have defined them, total current is I. So, I said that na, that suppose your differential input is increasing this side and decreasing this side. So, this I will increase this side and decrease this side, but this should look symmetrical. This is the main advantage of the differential amplifier, both of the MOSFET are symmetrical, tail current is fixed, RD of both branch is symmetrical. So, this whatever the output, they always should be symmetrical. symmetrical and out of phase. So, if one is increasing, other should decrease. So, this is our current, that should be right, that we discussed, that if one current is increasing, other current should decreasing, that is, this plot is telling the same thing. And when they are same, when the V d is 0, right, V d is 0 means your total voltage is VCM plus V d. So, when V d is 0, which point it is 0? Center point. Then what is remaining? Only VCM. If only VCM remains, I 1 is equal to I 2 is equal to I by 2. So, that is the middle point. Now, this is they have divided it with I, you can do that or you may not do that. If you divide it to I, your range is 0 to 1, middle point is 0.5, and this also, this V d you can divide with V o v or not. So, this is called normalization, that is it, nothing else. Okay. So, this is my differential input versus differential current plot. So, this is the differential current plot versus differential input plot. So, next is large signal operation. So, what is the meaning of large signal operation? When I am giving full, when we are considering the total instantaneous voltage, means DC plus AC, that is your large signal. When I am considering all signal, that is actually large signal analysis, and when we are considering only AC, that is my small signal analysis. So, instantaneous value DC plus AC, or generally we neglect AC, only the DC is considered large signal analysis. If we consider what is the output voltage for input current, that is DC current, that is large signal operation. So, large signal operation, what we will do? We will check what is my input voltage, what is my output voltage. Okay. So, same I said now only one equation. So, you will be always seeing that only one equation. If you know this only one equation, you can solve it. Only thing is that in one terminal I am giving VGS 1, other terminal I am giving VGS 2. So, in one branch I am getting ID 1, other branch I am getting ID 2. So, what I will do? I will calculate this ID in terms of VOV, because it is easier. Okay. So, what I have done, this input voltage difference I have termed it as VID, input voltage difference. Okay. And this previous calculation you see VOV, VOV is easier to calculate. Okay. ID and VOV, this equation VOV is equal to square root of this. So, that form you if you take, so I will come as a square root, right. So, then it will be easier to calculation, easier for calculation. So, square root of ID 1 minus square root of I 2, that form we have taken this. Okay. Now, we have one information given that ID 1 plus ID 2 is equal to I. This information we will try to utilize. Now, if you make a square of this, suppose you have A minus B, if you make it a square, what you get? A square. So, you get A plus B, na? This term we will calculate, we need to calculate this. This term you see is given, I 1 plus I 2 is given, right. Getting my point. So, why we are doing this? So, that we will try to make a square, then this term will be, we already know, then what is unknown? This unknown we can solve now. Okay. So, this square root of 2i is square root of ID 1 ID 2, this is this equation. So, we can plot that now. So, that term, from that term, this term we will put it here and we will calculate the ID 1 and ID 2, that is actually plotted here. ID 1 is equal to I by 2 plus some expression, and what is this expression saying? That if VID goes positive, ID1 will increase, if VID goes negative, ID2 will increase. Differential, right, opposite way should happen. So, this can be calculated from this equation. So, this plot is coming from this equation, and this equation we can do only from this current expression. Okay, step by step if you follow, we will arrive to this plot, and this plot which correspond to this equation will correspond to this plot. This plot we already have described. Now, you see there is one variable in this equation, that is VOV. What is VOV? VCM minus VT, VGS minus VT, na. So, if we want to change the slope or if we change the range, only control we are having VOV. In this equation you see I is fixed. Okay. So, VOV if we vary, we can vary this, right. So, suppose I want to increase my linearity range, I want more range, where it is more flat, when VOV is higher. So, if I want more linear range, what I should do? I should use more VOV. VOV increases the linearity. Okay, if I increase VOV, my range is also increasing, you see, but at the cost of what? It is getting flat, na. This is having more gain, this is more steep, this is having less gain. It may be wider, this range is more, this range is more here, but gain is less. Okay. So, if I want to increase the linearity range, I can do that by increasing the VOV. VOV means VGS minus VT. How we can do that? If we increase the common mode voltage, we will get more VOV, but at the cost of reduced gain and reduced GM. GM also, if you think of VOV, it is inversely proportional to VOV, right. So, if VOV is increasing, GM will fall, transconductance will fall, and transconductance is your gain, minus GMRD is your gain. So, if GM is falling, gain will also fall. Okay. How you can increase VOV? See this equation, VOV is, if you want to increase this portion, this W by L you have to reduce, na. Suppose current is fixed, you want to increase VOV. So, if you other technology parameter you cannot change, K and dash you have no control. So, you have only control is W and L. So, W by L if you reduce and your total current is constant, it has to increase VOV, otherwise current cannot remain constant. Okay. So, that you can do by using a smaller W by L ratio, considering what? Considering bias current is constant. So, now this is your circuit, and if I want to do the small signal analysis, that okay, DC wise we have seen that DC gain is 0, VD1 is equal to VD2. So, subtraction is 0. Now, we have to see the AC wise. AC wise what should be our gain, that we have to calculate. Now, if I have a current source while doing the AC signal analysis, this current source what we said, if there is a DC voltage source we should short it, if there is a current source we should open it, remove it. So, if we remove it, you see this, if I change this voltage, what is changing? Actually current, right. This voltage was connected to VDD, so we will short it to ground, because it is AC analysis, all the DC sources should be removed, right. So, if del I is changing, what is del V? Del V is equal to del I into RT. You just do the calculation, na. V0 is equal to VDD minus ID RD. You take a derivative of this. del V is equal to derivative of VDD, VDD is a constant, it is 0, it is del ID by del V in, this is termed as transconductance GM. So, we should get that na, agree. Have you seen this equation before? Which circuit? Common source. So, does it look like the common source? Yes, na. I am taking output from the drain terminal, source is common. So, this is a like a common source amplifier. If we replace this current source with a resistance, this will be, and separate these two branch, this will be a source degenerated common source common source amplifier, agree. So, if VD is changing, what is actually changing? I is changing. What is I? GM into VGS. So, what is output? Delta I into RD. So, that is coming as GM into RD, na? Getting my point. So, now this node one interesting phenomena is there. Suppose I am increasing this V by delta V amount. So, this VGS is increasing by delta V and I am decreasing this by delta V. Okay. So, this source voltage, suppose this source voltage, because of this it is increased by delta V, and because of this voltage this will decrease by delta V. So, what happens to the source voltage? This remain flat, agree. I am giving a differential input. So, this source voltage, that we can think that virtually this is at a AC ground, it is not changing. But this node voltage, if this is a ideal current source, this node voltage virtually it should not change, it should be constant. Why? Because one is increasing, other is decreasing. So, this node voltage will be always balanced. So, this concept is known as the half circuit concept. We can consider this as a ground, this node we can consider as a ground, and we can break this as two part, two equal, and this is a symmetrical circuit. So, if we calculate one branch, we can calculate it for other branch. So, in one branch let us consider that VID by 2, other branch it is minus VID by 2. So, total voltage is VID. So, if it is VID by 2, my current is actually ID by 2. So, one branch it will be minus GM by 2 RD, other branch it will be GM by 2 RD. If we subtract them, what we will get? Minus GM RD. Minus you can cancel depending on which branch you are taking first. So, this will be our small signal gain. Okay. And if we consider the channel length modulation, it will be GM into RD parallel R naught, just like the common source. So, its response is, sound signal response is just like common source response. Why? Because of this half circuit concept. Now, this resistive load we can change it with active load, this is known as the active load. How we can design a active load? We can provide a fixed voltage to a MOSFET. If I provide a fixed voltage to a MOSFET, this will behave like a current source, na? And if it is behave like a current source, I have a high output impedance. This R naught will replace this RD. Okay. So, this is, you see, these two MOSFET, they are same, identical, and they have connected to a fixed voltage. So, they will behave like a current source, and we can consider that they have a R naught. So, this R naught will be now my, this will replace my RD. So, what will be my gain now? If this is RO1 and if this is RO3, so this is GM1 RO1 parallel RO3. Okay. I am not getting into details because we have discussed this in details in common source single stage amplifier. Okay. So, this is known as the active load, previous was resistive load, passive load, this is active load. We can also use cascode, we can use 2 stage to increase the gain. Okay. Output impedance will be increased because I have now have 2 stage. So, output impedance will increase. So, correspondingly GM into R out is increasing. So, gain is also increasing. So, we have already discussed that if we use the common mode, it is 0, ideally it is 0, but it is in reality it is not exactly 0, that we can model this current source, we can model with 2 RSS resistance, and we can do the same analysis and calculate this small signal voltage. So, this will be roughly RD by twice RSS. Okay. So, now if we consider that RD is one branch, it is RD, and another branch it is RD plus delta RD, then we will be in this equation it is RD by twice RSS, okay, common mode signal. So, this will vary by delta RD, and we know in differential it is GMRD. Okay. We will divide this with this RD by twice RSS. So, we will get this ratio will get twice GM RSS by delta RD by RD. So, you see this twice GM is large, RSS is large, and you are multiplying with again 2. So, this CMRR is generally very high. In simple, you remember that common mode gain is 0. So, CMRR should be ideally very high, but in reality because of this mismatch we can calculate there are small common mode gain and we can recalculate this CMRR as very high. Okay. The current mirror we have discussed, that also you can use as a load and you can put it there. So, we have completed the differential amplifier section. I will advise you to go through this, and if you have any doubt please contact me, okay, we can discuss.